All right, so we're going to start with number one here. The pirate ship being chased by the space police, and they give us their velocity, their speeds in kilometers an hour, and they need 25 minutes to run the fast light drive so you can jump into hyperspace. So we're looking at how much time for the police to overtake the pirates. How many different frames of reference are there here? Any guesses? I'll give you a hint. Less than 10. How many do you think? 3. Yeah, there's 3. Because there's 3 things that are moving at different velocities. There's the space itself, there's the police, and there's the pirate. And we can look at this from any of those 3 frames of reference. We just need to pick which one we are, because all of those velocities are going to be different based on the frame of reference. Could you guys, whoever was in the file cabinet last, could you just close it? Thanks. So, once you ask for this one, which frame of reference do you want to do it in? Question asked, can they, how many minutes does it take to catch up to the pirates? In the police's frame of reference? Sure. Let's do it in the police's frame of reference. All right. So that's probably some of the first things I'd have here. This is number 1. I would probably put something like there are 3 frames of reference, and those I always just abbreviate capital F, lowercase o, capital R. In the police frame of reference, space is moving to the left, and so is the pirates. The police are not. So that's probably where I would start off with my why for this, recognizing that there are 3 different frames of reference that I could use, that since we chose to do it from the police's, oh, sorry, not really truncated, from the police's frame of reference, then space is moving to the left, and so is the pirates, and the police are not moving. So what I might even draw is what it looks like from that frame of reference. Let's see. The police are just sitting there. The velocity of space in reference to the police would be that direction, and then we can do our pirates, and this would be the velocity of the pirates with respect to the police, would also be in that direction. And this is just the police here. Velocity of space with respect to the police. I wish they called them something but pirates so that I could have more. Dale, there are. Yeah, there's 2 over there. 2 over there if you want to work on the assignment at all. Feel free. Or use your phone, yeah. And so, what we're given, we're told that we have the velocity, let's see, we're told the velocity of the pirates with respect to space. So the velocity of the pirates with respect to space is 1263 kilometers per hour. And we're told the velocity of the police with respect to space is 1407 kilometers per hour. Which direction do you guys want to call positive? To the right? Okay. So we'll call this direction positive, which means that both of these should be listed as positive, right? Because both those are given to us as moving to the right. Yes? Okay. So, now's the time to pull out my equations from my equation sheet. From my equation sheet, I have that the velocity of AB equals the opposite of the velocity of the A. And so if the velocity of the police with respect to space is positive 1407 kilometers an hour, this equation tells me the velocity of space with respect to the police is negative 1407 kilometers an hour. Doesn't change the magnitude of it, but reverses its direction. Yes? Good, so I know that one. I want to know the velocity of the pirates with respect to the police. So I'm going to use my relative motion equation, which says that the velocity of AB plus the velocity of BC equals the velocity of AC. Remember we were doing that the other day, the second day that we were going over stuff, right? Okay. I want to end up knowing the velocity of the pirates with respect to the police. So that means I need the pirates with respect to something blank, the police, something with respect to the police, and like the B's, the inners have to be the same, so let's do it with space. So if I know the pirates with respect to space, add to that space with respect to the police, I'll get the pirates with respect to the police. Does everyone see my setup there? Makes sense. How I picked where to put things? Because there's other ways you could do it. But this, so pirates with respect to space, I was given that it's positive 1263 kilometers an hour. So this is positive 1263 kilometers an hour plus space with respect to the police. Oh, we did that right up here. So plus negative 1407 kilometers an hour. And that's going to equal the velocity of pirates with respect to the police. Huh? Oh. So I need to add those two numbers. 1263 plus negative 1407. So 1263. 1263. Try that again now that I don't have the marker in my hand. Plus negative 1407. Negative 144. Kilometers per hour. And so, if we look at our situation again, the two meet up when they're at the same space, right? So we need to figure out, since the police are just sitting there, how long does it take the pirates moving at negative 144 kilometers an hour to move backwards to the police, right? Because in our frame of reference, the police, we're just sitting there, they're just coming towards us. So to do that, I use V equals V naught plus V initial T plus 1/2 A T squared. Any acceleration? Nope. We'll say we start at position 0. So I want to know it's got to move 50 kilometers. It's moving at, actually it's got to move negative 50 kilometers, right? Because it's got to come left 50 kilometers equals negative 144 kilometers an hour times t. Solve for t, and I get, let's see, that would be 50 divided by 140. And I get, oh, because, sorry, yeah, I took a little shortcut in my head because I had negative divided by negative. I don't feel like writing this number again. No. Because what units is that in? Hours. And what do they want it in? Minutes. So how do I get from hours to minutes? How about multiply by 60? Times 60. So I get 20.8 minutes. Let's see if that's right. And if that is right, will the pirates be able to escape? No. Let's see. Yay! Yay! Alright, so number 3 here, we've got a boat across the water. And the boat is attempting to go straight across the river, but the river is also going to add its velocity to the boats. So you're going to end up with this resultant velocity like they've shown you here going down the river. I think the other day we talked about everyone is clear on upriver, downriver. Yes? Okay, good. So the what I would put for my y here, I'm probably going to draw that diagram, but I'd also put things like let's see what they have. One big fact that a lot of people forget: the displacement and velocity must be in the same direction. They must be in the same direction. If your speed, there's no way for your displacement and your velocity not to be in the same direction. Is that it? We're really done? Wow. All right, so we were working on number 3 before lunch. Now we're back. And the next thing I would do in my y here is actually do a vector diagram. They nicely supplied one for us, which is nice. Because I think that shows being able to do that is good understanding. You could also, if you didn't feel like doing that, you could write something like the velocities combined as vectors, so direction is important. All right, because it's very important what direction these things are pointing in. All right, so let's see what information they can tell us. They tell us the boat with respect to the water for me is 2.3 meters per second. And they tell me the water with respect to the shore is 1.3 meters per second. You think back to that packet we were doing the other day, where they had all the different ways of saying how those related to each other and everything like that. So, multitude of ways of saying those. And now they want to know what the velocity of the boat is relative to the shore. So if I'm starting with my general equation, that triangle is formed from the velocity of the boat with respect to the water, plus the velocity of the water with respect to the shore is going to give us the velocity of the boat with respect to the shore. And you can see that in the triangle, right? You add the two perpendicular vectors and you get the hypotenuse there of that right triangle. And since it is a right triangle, we want to find out the magnitude of VBS. We can use Pythagoras, and we also want to find out the angle here. And the one thing to be very careful of to check the boat points, what is the velocity, magnitude relative to the shore. So they don't just want that angle here, they want that angle plus this angle. How big is this angle here? Right, 90 degrees, because it's a right angle. So they actually are looking for the direction relative to the shore, not relative to straight across. If they just wanted theta, they would say relative to straight across, but they want it relative to the shore, so it's 90 plus theta. All right, be careful of that, what you're referring it to. So let's first find out how big this velocity is, its magnitude. To do that, we're going to use our good old friend Pythagoras. B squared equals c squared. So 2.30 meters per second squared plus 1.30 meters per second squared equals VBS squared. And I find out my speed relative to the shore. Notice I didn't put the vector mark on it by doing 2.3 squared plus 1.3 squared, and I get 6.98 square root that, and I get 2.641. And round that to 2, 3, 6 figs, 2.64. So 2.64 meters per second. That's going to be speed. Now I need to do my direction. My direction, I'm going to look for theta. And I know the side opposite theta. That's the 1.30 meters per second. I know the side adjacent to theta. That's 2.30. And if I think about SOHCAHTOA, tan of theta, the toe part, is opposite over adjacent. Alright? So, tan of the angle I'm looking for, theta, is my 1.30 meters per second over my 2.30 meters per second. I need to get theta by itself, though, so I'm going to do the inverse or arctan of both sides. We did this a bunch when we did the vector. Tan to the minus 1 of 1.30 meters per second over 2.30 meters per second. And then I use my calculator to find out theta. I grab my calculator and I do second tan, which gives me the inverse tan. 1.3 divided by 2.3. With my parentheses. And I get that because I forgot that I was in radians. In my mode. Now I'm in. And what's nice is I can arrow up and enter, and then enter again, and I get it, rather than in radians, I get it in degrees. 29.5. I get 29.5 degrees. So my final answer here for this part is going to be the 2.64 meters per second. And add a direction. Remember, they wanted it reference to the shore. So I'm adding 90 to my answer for theta. So that would be 90 plus 29 is 119.5 degrees, or I should really write that as 120 degrees after I've rounded. Let me see if that's correct. After all it is done. 64. Yeah. That's where I'm wondering if their programming, they wanted, I know what they did. What they were actually, I believe, let me take a guess here. They were thinking of this angle here. Call that, I don't know, alpha. They wanted angle alpha. They weren't real clear on this. So how would alpha be related to theta? Subtract theta from 90, right? So let's try that. Well, I don't like how they were unclear, so we'll get rid of this part. And let's see, 90 minus theta. 90 minus theta would be 60.5 degrees for mine. Let's see if the answer keeps like that better. I bet it does. Huh? Dude, the only reason we ever got a radian was I had my calculator screwed up. Notice I didn't write down the radians anywhere. That was called Mr. Cochran forgot to switch the mode of his calculator like he always tells you to do. So, they did want that angle that was 90 minus theta. They wanted alpha rather than 90 plus theta. They just weren't real clear, so this was alpha. And all right, let me pause the recording so I can come over to you. All right, let's do the second part of this one. Because in the second part of this, it says, what will be the position of the boat relative to the point of origin after 3 seconds? So now here's the big question. Does the fact that the boat's moving downstream affect how the boat is moving across the river? No, they're completely independent of each other. And that might have been something I put up in my why, once I realize it now, is that, the two velocities are independent of each other. All right, so going downstream, I'm moving at, let's see, my velocity of I move with the water to the shore, which is I'm moving with the water downstream, was 1.30 meters per second. I'm going to use my good old equation d equals d naught plus v initial t plus 1/2 a t squared. No acceleration. D equals 1.30 meters per second, and I move at that speed for 3 seconds. So I get a D of 3.90 meters. Then I look at across the river. So this is down the river. And now I'm going across the river. Velocity of the boat with respect to the shore across the river was, for me, 2.30 meters per second. Be careful, use your own numbers. D equals D naught plus the initial T plus 1/2 AT squared. No acceleration. Start at 0. D equals 2.30 meters per second for 3.00 seconds. My D is 6.90 meters. I think those would be right. Is that far enough? So we're going to do number 5. Woman starts to swim directly across the river. Her speed of stretch of water is this. We're going downstream speed is this. How much time does it take her to cross the river? Does her being swept down the river affect her velocity across the river? No, because they're perpendicular to each other. So that's where I would start. This is number 5 with my y. Her velocity downriver does not change her velocity across river, since here's my little symbol for perpendicular. That's what I use for the word perpendicular. It's kind of like 2 right angles to each other. That's one of those weird things. So then I would probably do a vector diagram here also. I'd have my river, happy little river. She's swimming this way. Velocity to the swimmer relative to the water. I'd add to that the velocity of the water relative to the bank. And I would get the velocity of the swimmer relative to the bank. Just like we had last time, just this time, I've got to do it myself. So, the velocity of the swimmer relative to the water is 1.3 meters per second. I think, right? Did I read the wrong one? 1.3. But it's a 5.6 kilometer wide river. So the distance is 5,600 meters. Be careful, watch, they switched units on you, right? 5.6 kilometers is 5,600 meters. So that's across the river, so higher. I'm going to use D equals D naught plus V initial T plus 1/2 A squared. No acceleration. Say she starts at 0. I'm listening. I read my problem, and it tells me directly across a 5.6 kilometer. So I change that to meters before I make the mistake of having unlike units. There's 1,000 kilometers in a meter. You learned that in middle school. You know that. 1.3 meters per second. Next time. Figure out my time. That's what they want to know, right? Yeah. So I'm going to go 5,600 divided by 1.3. No. Well, and if I'd made that mistake, right, I get 4,307. Does it make sense it would take about 4,000 seconds to get across a really wide river? Well, let's try it the opposite way. Does it make sense if I'm going across a 5,600 wide, which is like a little over half a mile wide river, that it would take me 2 times 10 to the negative 4 seconds? No, that doesn't make sense. But it makes sense 4,000 some odd. 4,310. Yep. That was my distance in kilometers, yes. Yes. Kilometers to meters. Yep. I got that right. How far downstream will the river carrier by the time she reaches the other side? Ah! What do these two motions have in common? I'll answer you. Time is same for both motions. Remember, they share a common time, right? She's got 4,310 seconds to go across the river. That's how long she has to go down the river, like a projectile. How much ever time it has to go out, it has that time to go up and come back down. So I'm going to start with my favorite equation, especially when I don't have acceleration. And I'm looking for D. I know my V initial 0.91 meters per second. I know my time now, 4,307.6969 seconds. I get a D of enter times 0.92, and I get 3,963, which to 3 sig figs would be 3,960. 1,960 meters. Let's hope that's right. Yay!